Division 2, yes or no, please? Please confirm.
No, sir, not yet.
Okay, then I think
We are completed in CV by CP.
Okay, CV by CP. So that means we not started the application of the first law to the non-flow system. Yes, isobaric and isochloric process we not completed. Please confirm. Okay, so in the today's lecture, we'll try to cover the application of the first law to the non-flow system. In this system, we'll try to understand how the first law, that is Q is equal to Q minus of W is equal to del U, is applicable to the non-flow system. So what exactly mean the non-flow system? How you will differentiate between the non-flow system and the flow system? What is the difference between the non-flow system and the flow system? Yes? Anyone?
Repeat again.
What is the difference between non-flow system and flow system? Non-flow system, this basically we call as the closed system, is it? It is called as closed system. And this flow system we call as open system. Now, in the closed system, most commonly studied the closed system is nothing but called as the piston and cylinder arrangement. So this is the cylinder and this is the piston, and this piston will reciprocate inside the cylinder. Okay, we will have some gas or working substance or working fluid inside the system, and this piston will reciprocate to and fro in the cylinder, and this gas will get compressed and expand. And while doing this thing, we allow the transfer of energy from system towards the surrounding, but we not allow the transfer of mass from system to surrounding. The mass should be there inside the system. But in the case of the open system, suppose the example of a pump, then what is the function of pump? The function of the pump is to deliver the water from low potential, that means from low head towards the high potential. So in this case, the energy at low potential is different than energy at the higher end. So transfer of energy takes place from one end to the another end. At the same time, the particular fluid also used to move. That means the matter or mass of the fluid also used to move inside the system and also move outside towards the system. So this is called as the open system. The first law of the thermodynamic is basically applicable to both the system. The first law is nothing but called as law of conservation of energy. So if you're going to talk about the first law, what the first law tells us, energy is neither created nor is going to be destroyed. Okay, so Q is equal to del U plus of W. This is called as the first law, and this is applicable to the closed system and as well as to the open system. Now, these systems that is called as closed system, first we'll call as the non-flow system. So we'll study the application of this first law toward the non-flow system. Hope we not completed the isobaric and isochoric process. Please confirm. Lastly, yes or no, please? Division 2?
No, sir.
No,
sir.
We completed Cp by Cv is equal to gamma.
Yes, sir. That's completed.
That we completed in the last lecture, and
Yes,
we not completed the application of first law to the isobaric and the isochoric process. Okay.
Yes, sir.
Okay. So the application, write down. Application of the first law to the non-flow system. In this case, first we'll discuss the system called as reversible constant volume process. Reversible constant volume process. So here we'll consider again a piston and cylinder arrangement. This is the cylinder. This is the piston. Piston will reciprocate in the upward direction. But in order to maintain the process at constant volume, we provided the stopper over the head of piston. And here we have the working system called as gas. The heat will start to add with the help of the heat source. Now, when the heat transfer takes place from the source towards the gas, then obviously the gas will expand and there will be built up of the temperature and there will be built up of the pressure. At the same time, when the gas expands, the gas wants to apply the pressure force on the head of piston and want to move the piston in the upward direction. But here, by providing the stopper, we are maintaining the volume constant. That means on the thermodynamic plane called as the PV plane, the pressure will build up from point P1 towards the point P2. So these are the 2 points called as P1 and P2 where pressure will build up. What about volume? V1 is equal to V2. So if you consider M as the mass of the working substance, then application of first law is Q is equal to U2 minus of U1 plus of W. This is our first equation number 1. Now, what is the work done in this case? Yes, anyone? What is the work done? Work done is equal to P multiplied by dV. What is the work done in this case? Yes, anyone? Am I audible? Am I audible?
Yes, sir.
So what is the work done in this case? From point 1 to point 2, work done is equal to pressure multiplied by change in volume. Volume is V1 is equal to V2 as volume is constant. So what is the work done in this case?
Zero.
Work done is equal to 0. Okay. So work done is equal to, because there is not any change in volume. Okay. So P multiplied by dV is equal to what we can say 0. So dV is equal to 0. So work done is equal to 0 for 1 to 2 process. So in this particular case, the value of Q is nothing but called as U2 minus of U1 plus of 0. What that mean? That means Q is equal to change in its internal energy, that is called as del U. Now, from the Joule's law, we also try to understand that this del U, the del U, 1 minute. From this Joule's law, we also try to understand the Q is equal to del U, and this del U is equal to what we can say CV multiplied by T2 minus of T1. Okay, so we can say that Q is also equal to CV multiplied by T2 minus of T1. For m kg of working substance, we can say that Q is equal to m multiplied by CV multiplied by T2 minus of T1. So in this particular analysis of first law towards the closed system, we try to understand that work done in case of constant volume process, work done in the case of constant volume process is always equal to 0 as V1 is equal to V2. At the same time, Q is equal to change in its internal energy, that is called as Q is equal to del U, or del U is equal to Q. And at last we try to understand that del U is equal to your mcv multiplied by T2 minus of T1. At the same time, when we'll explore the unit number 5, that is called entropy, there will be change in what we can say in the entropy, that is called del S. So at that time, we'll explore, we'll again revisit this particular process and we'll try to understand what is change in entropy in that particular case. But as for the first unit number 1, we'll only limit our discussion that for the first unit, for the reversible constant volume process, work done is equal to 0, Q is equal to del U, and del U is equal to mcv T2 minus of T1. Any doubt in this? Please ask. All of you with me? Yes or no, please?
Yes, sir. No doubt.
Sure.
Now the second process is called as reversible constant pressure process. It is called as reversible constant pressure process. So in the last process, we try to maintain the volume constant by providing the stopper over the piston so that the piston should not move in the upward direction. But now here in this case, when you want to maintain the what we can say the pressure constant, then we'll remove that particular stopper so that the piston must able to move in the upward and downward direction. But in order to maintain the pressure constant, we'll put the weight over the head of piston. So this is cylinder, and here this is nothing but called as the piston, and over the head of piston we'll put a certain weight. The stoppers are removed. Now what we'll have here are the gas inside the system, and gases get heated with the help of some heat source. Continuously heat will get added up. Because of that, the piston will change its position and it will move from one position towards the other position. The weight will be same, but there is a change into the particular volume. But what about the pressure which is going to exert on the head of piston? The pressure here and here in both the cases, whether the volume is V1 or whether the volume is V2, pressure is same because weight is same. So if you want to draw this particular process on the thermodynamic plane, that is called as PV plane, will get a line like this. Yes or no? Because pressure is same. So pressure at point 1 is equal to pressure at point 2. So associated volume is V1 and associated volume here is V2. Any doubt in understanding the PV diagram? Any doubt, please?
No, sir. Clear.
Okay. So we'll consider the unit mass of working substance. Working substance. Now Q is equal to, application of first law, Q is equal to your U2 minus of U1 plus of W. This is our equation number 1. Now, what is net work done? Net work done is equal to integration 1 to 2 P dV, and the dV changes from what we can say the V2 minus of V1. This is our second equation. Now,
The pressure is constant.
yes, pressure is constant because look here at this point, this is the cylinder and this is the piston. We are adding the heat. The piston is moving in the upward direction. Because of the addition of the heat, gas will expand. The volume will change from V1 to your V2. And whatever the weight we are providing over the head of piston, that is constant. That is not going to change. We are not experiencing any variation inside that particular weight. So the expansion of this gas takes place under the constant pressure. Whatever the pressure is there at this point, the same pressure the gas will experience at this point. And because of this reason, we can say that when the process takes place from point number 1 to point number 2, we'll able to maintain the pressure constant. That is P1 is equal to your P2. That means there can be change into the volume, from V1 to V2. But what about the pressure at point 1 and pressure at point 2 will be same. Getting?
Yes, sir.
So work done is equal to PdV, V2 minus of V1. So in this case, the what we can say, Q is equal to U2 minus of U1 plus your P V2 minus of V1, or we can say it is nothing but U2 plus this PV2 will add is U2 plus PV2, okay, minus this is U1 plus PV1. Now we are moving towards one more thermodynamic plane, a thermodynamic the quantity which basically gives the addition of internal energy with the flow work. Now, what is U2? It is the internal energy at point 2. What is P multiplied by V2? It is the flow work. What is U1? Internal energy at point 1. What is PV1? It is the flow work at point 1. So the addition of internal energy plus flow work, that is PV2, okay, is nothing but called as enthalpy. So it is called as Q is equal to your H2 minus of H1. Okay, enthalpy is nothing but the addition of internal energy with your flow work. So this Q we can also define is nothing but the difference between the enthalpy at point 2 and enthalpy at point 1. Now, this particular enthalpy, so when we'll explore this unit number 2, that is properties of pure substance, we'll talk about more about the enthalpy of the water, enthalpy of the steam, and enthalpy of a dry steam, enthalpy of the wet steam, superheated steam, saturated steam. We'll talk about more about that. This Q, and the processes happen at constant pressure. So H2 mass of H1, this is equation number 3. As processes happen at constant pressure, we know that Q is equal to M multiplied by C multiplied by del T. Yes, in the specificate we learned. So here the Q is equal to M multiplied by C. So here C will get replaced to the Cp because process happen at constant pressure and the temperature is nothing but called as T2 minus of T1. Okay. So in this case, this H stands for specific enthalpy, and the T2 and T1, they are basically related to temperature gradient what we are able to experience because of this particular process. So in this case, we can say that the work done in the constant pressure process, this work done is equal to P multiplied by your dV 1 to 2, which is equal to P multiplied by V2 minus of V1. Then this Q is equal to your H2 minus of H1, and this H2, or we can say del H, is also called as the Cp multiplied by T2 minus of T1. So for unit or for m kg of mass, this del H, okay, is nothing but mCp T2 minus of T1. Okay, this is called as total enthalpy, and the small del H is nothing but called as specific enthalpy. Okay, specific enthalpy, that means kilojoule per kg. What should we read it here? Kilojoule per, you can say the kg. Okay, here only the what we can say kilojoule. Okay, all of you with me? Yes or no, please? Any doubt in this? In the second process?
No, sir.
So in the first process, when the process happened at constant volume, work done is equal to, yes, work done is equal to 0. Then change in internal energy is equal to, change in internal energy is equal to, in the first process, constant volume process,
mCv T2 minus T1.
yes, mCv T2 minus of T1, and Q is equal to del U. Okay. Now, when the process happened at constant pressure, the work done is equal to P multiplied by V2 minus of V1. Q is equal to H2 minus of H1. and del H is equal to mCp T2 mass of T1. Now, if you compare the del U and del H, what is del U is nothing but called as U2 minus of U1. And what is del H? Del H is equal to what we can say H2 minus of H1. Okay. So many times students used to make a mistake that at the place of U2 minus of U1, they used to write down U2 minus of U1 is equal to your, okay, for the unit mass, they used to write down U2 minus of U1 is equal to Cp T2 minus of T1. And H2 minus of H1, they used to write down the Cv multiplied by T2 minus of T1. So it is completely wrong. Del U is always we need to express in terms of Cv, and del H we always require to express in terms of Cp. Okay. Now, can anybody explain me why we need to express the del U in terms of Cv only? Why not in terms of Cp? Why not in terms of Cp? Yes. All of you getting my question? Yes or no? All of you getting my question? क्वेश्चन समझ में आ रहा है क्या आपको?
Yes, sir.
So why we are always expressing the del U or internal energy, okay, in terms of Cv. In the last lecture, okay, anyone want to give the answer for this question? Del U only in terms of Cv? Abhishek 042.
Yes, sir.
Yes. Can you tell me why we are always expressing the del U in terms of Cv? Okay, 044, Bharat.
Sir.
Yes. I'm not getting?
I don't know.
Don't know. Okay. Darshan 049.
यस सर.
बोलिए.
तो अपन ने सर कल वो प्रूफ किया था ना, डेल्टा यू एनसीवी डेल्टा टी होता है.
हाँ, but Q. Why del U is always in terms of Cv? Basic question, fundamental. What you are saying is right. हमने proof कर दिया था, but why we always express a del U in terms of Cv? Why not in
because
Cv?
of constant volume?
Because
Sir.
of constant volume. Okay. Because of constant
Internal energy.
volume.
सर इंटरनल एनर्जी कांस्टेंट होती है ना सर, इंटरनल एनर्जी कांस्टेंट होती है सर, तभी सर एनसीवी डेल्टा टी लेते हैं.
हाँ, but which law basically gives us this particular input to you? Which law?
फर्स्ट लॉ.
First law. Other than that, not a first law. We studied one experiment. Name of that experiment is Joule's experiment. Yes or no? Where the heat, we are able to convert the work done into the heat and heat the heat into the work done. In the Joule's experiment, what the Joule's law tells us, the internal energy is always a function of absolute temperature only. And by studying that experiment, we come to know that we allow the weight to fall down, and because of when the weight fall down in the direction, the internal energy changes from U1 to U2. But when the internal energy changes, is there any change into the volume of that fluid in that particular beaker? No, there is not any change in the volume. That means the
Isochoric process.
Yes. So the process happen. What we can say, the process happen at constant volume, and there is a change into its internal energy. So internal energy is always the function of absolute temperature related to the process which happen at constant volume, and because of this reason, the U2 minus of U1 or del U is always expressed in terms of your Cv. Okay, del H, that means in this particular process that which happened called as constant pressure process. What is Q? Q is equal to M multiplied by C multiplied by dt. The process happened at constant pressure. So Q is equal to Cp multiplied by T2 minus of T1. So if we apply the first law to this particular process, then we come to know that it is nothing but equal to the change in its particular enthalpy, that is H2 minus of H1. And because reason, whenever the enthalpy comes into the picture, okay, when the process happen at constant pressure, obviously volume will not be constant. There will be change in the volume, there will be change in temperature. Okay, so change of enthalpy we always used to express in terms of what we can say in terms of Cp, and change of internal energy we always expressed in terms of the Cv. Getting all of you? Yes or no, please? All of you with me?
Yes, sir.
Yes,
So
sir.
at the time of calculation, at the time of what we can say numerical, when you solve the numerical, okay, by mistake, okay, because of the doing the calculation in hurry, okay, don't put del U is equal to Cp multiplied by del T. Remember, del U is always equal to Cv multiplied by del T, and H is always equal to Cp multiplied by del T. Okay. Now the third application of the first law is nothing but called as reversible, we can say constant temperature process, or we can say the isothermal process. Write down. Reversible constant temperature process, or it is also called as isothermal process. Okay, so in the isothermal process, it's called as isothermal process. Okay, this is taking a little bit time to save, so because of that these words are not. Okay. Isothermal process. Okay. So isothermal process means we are maintaining the temperature constant, okay, and we are basically trying to see the variation into its pressure and variation into its volume on the thermodynamic plane, on the PV plane. Okay. So in this process, we will have a piston and cylinder arrangement again, and the heat source. Heat source, the piston will be there, and inside that we'll have the gas. Okay. Now, if you want the expansion of these particular gases, the curve will follow this straight line, PV. This is point number 1 and this is point number 2. So during expansion of these gases, okay, in order to avoid the what we can say fall in temperature, the heat must be added to the system. So suppose that, take the example, if what we are having the working substance gas in the cylinder and gas started to expand, then obviously the temperature will drop down. So when the temperature will drop down, then obviously the temperature at point 1 will be different than the temperature at point 2. So we are not able to maintain the process at constant temperature. So in that particular case, the heat from the heat source, the heat must be get added into the cylinder in order to maintain the temperature constant. But because of the addition of the heat, if the temperature increases, that means again you are not maintaining that process called as at constant temperature. We need to take care that addition of the heat must maintain the temperature constant. The temperature should not increase and should not fall also. So in order to maintain the temperature constant, and if the expansion of the gas takes place, then obviously volume will increase from V1 to V2. So when the volume increases from V1 to the V2, at the same time expansion takes place, the pressure will drop down from P1 to P2, and there will be a drop down of the temperature. So we added the heat with the help of the heat source. And reverse is also true. That means during the compression, obviously temperature will build up. So in order to avoid the build-up of the temperature, the heat must be removed from the system. So we can have the system toward the heat sink. Okay, so that whatever the built up of the temperatures are, that must be get dropped down and it must transfer toward the heat sink. Okay, so heat source and heat sink we need to use in order to maintain the temperature constant. And in this way, we can maintain the temperature constant and we are able to see the variation of the pressure with respect to volume or variation of the volume with respect to the pressure on the thermodynamic plane. Okay, so we'll consider a unit mass of working substance, M, unit mass of. Why we are deriving all these equation? Because this time the IMU is going to conduct the offline exam, and in the offline exam, if you study the question paper pattern for the 8 to 10 mark, they used to ask all these derivation. Derive for constant pressure process, for constant volume process, for isothermal process, work done, change in internal energy, and the heat transfer. Okay, for 3 process, 1 mark for each term. So 9 mark, 8 to 9 mark question they generally used to ask in the examination. So with respect to the examination point of view also, this derivation plays a very, very important role. And at the same time, if you know the derivation, it will be very, very easy for you to go into the numerical. No need to mug up the formulas. Okay, only by knowing the process and their basic understanding, you are able to use these relations directly into the numerical. So that is the main importance that why we are doing all these particular what we can say the derivation. So don't mug up the what we can say the formulas. Okay, try to understand the methodology what we used in the derivation, and this will help you obviously in the examination and in the numerical also. Okay, let him save the material. So here, okay, give him 1 minute. Okay, yes. So here, considering the unit mass of working substance, we come to know that Q is equal to yes, Q is equal to the U2 minus of U1 plus of W. Okay, and U2 minus of U1 we can define as CV multiplied by T2 minus of T1 plus of W. Now, what is the value of T2 and T1 in this case? Yes, anyone?
Is equal to T.
T2 and T1 both are same. Okay, so what is the del T in this case? Is equal to 0. So what is the value of Q in this case? Q is equal to W. Yes or no? Q is equal to W. Getting?
Yes, sir.
Okay. Now, if the Q is equal to W, so this is our equation number, this is 1, and this is our equation number 2. Now we'll go for the work done equation. Okay. The work done is nothing but call it integration 1 to 2 multiplied by your PDV. Okay. And we know that for the constant volume process, the product of PV must be equal to, for constant temperature process, the product of PV is equal to C. Okay. So here, in this case, what is the value of P? P is equal to C by your V. Okay. So this equation that is called as work done is equal to integration 1 to 2 the PDV. This equation we come to know that it is equal to from 1 to 2, that is the V1 to V2. P is equal to C by V dV is equal to C log to the base C of V V1 to V2, or we can say that it is equal to C log to the base E V2 by V1. Okay, let me save this. Let me change the page. I think this Word document is hanged. So work done is equal to your C log to the base C V2 by V1. Okay. Okay, so I opened a new page. So we just now come to know that work done is equal to C log to the base C V2 by V1. This is our equation number, what we can say equation number 3. We know that C is equal to P1 V1 is equal to your P2 V2. Okay, so in our equation number 3, we can write down that W is equal to P1 V1 log to the base C V2 by V1. This is our equation number 4, or W is equal to P2 V2 log to the base C V2 by V1. So equation number 5. Okay. Now here so in this case, when you are going to talk about W is equal to P2 V2 log to the base C, W is equal to P2 V2 log to the base C V2 by V1. This is equation number 5. Now equation number 2, we know that Q is equal to your W. So what is W? W is equal to P1 V1 log to the base C V2 by V1. Now just now we know that P1 V1 is equal to your P2 V2. Okay, so V2 by V1 is equal to P1 by your P2. So this equation we can write down Q is equal to W P1 V1 log to the base E P1 by the P2. Getting all of you? Yes or no? All of you with me?
Yes, sir.
Yes, sir.
So
Yes, sir.
Yes, sir.
So in the reversible isothermal process, we learned the 3 basic equation. That means first equation is related to the Q. Q is equal to U2 minus of U1 plus of W. As U2 minus of U1 plus of, as you can say, change in internal energy is the function of the temperature, and we are maintaining the process at constant temperature. So U2 minus of U1 is always equal to 0 for the isothermal process. So change in internal energy, they can also ask that change in internal energy, prove that change in internal energy for isothermal process is equal to 0. So simply we need to explain this isothermal process and how we are maintaining temperature constant, and then state the Joule's law. And after mentioning the Joule's law, you can write down del U is equal to your MCV T2 minus of T1, as temperature T2 is equal to T1, so del T is equal to 0. So we can say del U is equal to 0. So change in internal energy is equal to 0 in case of the isothermal process. Okay. Then the particular your work done. What is work done? Work done is equal to, we can define work done in the form of P1 V1 or in the form of P2 V2. It totally depends on the your data, whatever data we are having at your particular end. So work done is equal to P1 V1 log to the base E V2 by V1. Now remember, log to the base E is ln. Okay, it is not locked to the base 10. So if I take a general lock, obviously you will make a mistake. So in the calculator, we have the ln key. Okay, so lock to the base E is ln. So many times at the time of calculation, the student used to make a mistake. Okay, they used to lock to the base 10. Okay, so this is locked to the base E, okay, which is equal to ln key in your calculator. So we need to do the calculation with the help of that ln key, not with the help of your general lock key. At the same time, we also come to know one more important thing in the case of the isothermal process, that Q is equal to W, because here the del U is equal to 0. So Q is equal to del U plus or W. So del U is equal to 0. So Q is equal to your W. And we try to define W in terms of V2 and V1. If you have the data for P1 and P2, you can also define this for the P1 and P2 also. Okay, I think this is again hanged. My documents are hanging. Okay, so the next process is nothing but called as reversible adiabatic process. Okay, so but before moving into the reversible adiabatic process, first talk out the three processes that is called as isobaric process, then what we can say isochoric process, and then isothermal process. Okay, so for this, what is the value of work done in the isochoric process? So first we'll talk isochoric process because we derived for the isochoric. Work done in the case of isochoric process where volume is constant, here pressure is constant, and here temperature is constant. Yes, anyone? What is work done in the case of constant volume process? Yes, just revise.
0.
Is equal to 0. Yes. What is work done in the case of isobaric process?
E delta V.
P delta V, or we can say P multiplied by V2 minus of V1. Very good. What is work done in the case of isothermal process? Just now we derived P1 V1 log to the base E
2 on V1.
V2 by V1, or P2 V2 log to the base E V2 by V1. Okay, so this is for work done. Now change in what we can say internal energy. Okay, change in internal energy in the case of constant volume process.
MCV delta T.
MCV delta T, or we can say it is equal to Q. Okay, so it is equal to what we can say Q, or MCV delta T. It is equal to Q or MCV T2 minus of T1. Okay, now in the case of isobaric process, the del U is equal to, yes, how you will define del U in the case of isobaric process? It is, बताइए, it is equal to, yes, anyone? Is it equal to 0 in the case of isobaric process? Del U, is it equal to 0? Yes or no?
So
Yes. Isobaric process, pressure is constant.
yes, sir.
तो टेम्परेचर 0 हो जाएगा क्या वहां पर? प्रेशर कांस्टेंट है आपका, वॉल्यूम चेंज हो रहा है, टेम्परेचर चेंज हो रहा है. सो del U इज इक्वल टू mCV del T ना, or we can say it is Q minus
Yes.
of W. It is always equal to Q minus of W or U2 minus of U1. You will have the value for this. We will have the value for this U2 and U1, or we'll have value of Q and we'll have also the value of W, because heat transfer will also be there and work done is also there. Remember. Okay. So this is very important. In the case of isothermal process, what is the value of del U?
0.
0. Very good. Why 0? Just now we talked about that. Why value of del U is equal to 0 in the case of isothermal process?
Delta T is 0.
Delta is equal to 0 because the process happened at constant temperature. Getting all of you with me? Yes or no, please?
Yes, sir.
Now we'll talk about the work done, del U, and then Q. Value of Q. चलो बताइए constant volume process. Q is
MCP
equal
delta
to,
T.
or isochoric process. Isochoric. Q is equal to, yes, in terms of W and del U.
Delta U plus
Del U.
Yes,
plus.
yes, only del U, constant volume process. Q is
Yes, sir,
equal
yes,
to
sir,
del
yes,
U, del U plus of W. Okay. And what is W in the case of constant volume process? 0. So what is the value of Q in the case of isochoric process? Del U. It is equal to del U.
Del U.
And how will you find del U? MCV T2 minus of T1. Just now we are already written here itself. Dekho, del U is equal to Q. So Q is equal to del U, which is equal to MCV T2 minus of T1. Okay. चलो अभी ये बताओ. In the case of isomeric process, what is the value of Q?
MCP delta T.
Yes, I'm not getting, please.
MCP delta T.
Yes, MCP. MCP T2 minus of T1. Okay. Now, in terms of enthalpy, yes, in terms of enthalpy,
H2 minus H1.
H2 minus of H1. Very good. Okay. And in the case of isothermal, in terms of W and del U, what is the value of Q?
W, sir. Q is equal to W.
Q is equal to W. Very good. Q is equal to W. Okay. And how we will define that W now in terms of
P
P1
delta
and
V.
P2? In terms of P1 and P2. V1 and V2 we define. In terms of P1 and P2. How will you define Q in terms of P1 and P2? Yes, बताइए. P1 V1 is equal to P2 V2. So V2 by V1 is equal to P1 by P2. देखो यहाँ पर W है ना, यहाँ पर P2
Yes, sir.
P1 V1 log to the base C V2 by V1. अब जो P1 V1 is equal to P2 V2 because temperature is constant. So V2 by V1 is equal to P1 by P2. Yes or no?
Yes, sir.
P1 V1 log P1 by P2.
Yes. P1 V1 log to the base C
P1 upon P.
by P1 by P2. So why we are talking about the different forms of these the formulas, because we need to choose the concerned formulas depends on the available data in the numerical. Okay. If you are using the formula of work done that P1 V1 log to the base V2 by V1, and if you don't have the value of V1 and V2, and if you know the value of P1 and P2, then directly we can use this equation. We can find out Q, and from that Q you can find out the value of W, and then V1 V2 depends. So we need to play with the terms. In the examination, they can ask for any unknown term. Okay, they may give you the data for Q, they may give you the data for del U, they may give you the data for W. Okay, and for the unknown terms we need to go. That means what is what is the pressure at the end of the isothermal process? So you need to find the value of P2. What is the volume at the end of the isothermal process? In the case of expansion, then V2. Value of V2 obviously greater than value of what we can say V1. Okay. We learn very basic equation. We learn a very basic equation in the case of specific heat. Okay. In the case of specific heat, that is Cp minus of Cv is equal to R. And we come to know that the value of Cp is always greater than the value of Cv. Why how you are able to conclude that value of Cp is always greater than the value of Cv? Cp minus of Cv is equal to R. The value of Cp is always greater than value of Cv. How you come to know this? Yes, anyone? Am I audible to all of you? Am I audible?
So
Yeah.
I'm not getting better. Value of Cp is always greater than Cv. Many times they used to give in the examination only the values. We need to identify whether it is Cp or Cv. So larger the value of whatever the given value, that is Cp. But why value of Cp is greater than value of Cv? That is my main question. Yes? Anyone?
Sir, because in CV work done is 0.
In the Cv work done is no, not like that. Not. Look here, look the basic equation. The value of Cp is equal to R plus Cv. No? So always in the value of Cv, you are going to add the value of gas constant. Okay. And what is the gas constant? Gas constant, that is R, is equal to your R naught. R is equal to R naught by M. This we learned. And what is R naught? Is a universal gas constant. So universal gas constant divided by molecular weight. If you're going to talk about that, then we are basically able to get the value of gas constant. So whatever the value of Cv is there, that is specifically at constant volume, in that you are always going to add the value of R. Okay. So it is the value of Cv is always in the addition of the value of Cp is always in the is basically having the addition of gas constant plus the Cv. So many times why I'm giving the putting this question to you, because many times in the examination they used to give the data only for the specific hits are the Cp, the specific hits are this and this 1.05, 0.718 kilojoule per kg Kelvin. Now we need to identify whether it is Cp or whether it is Cv. So whatever the larger value is there, that is always Cp. Whatever the lower value is there, that is called as Cv. Okay. So in the value of Cp, it is R plus Cv. Cp by Cv is equal to gamma, which is nothing but equal to 1.4. Getting all of you with me? Yes or no, please?
Yes, sir.
Okay. So in the today's lecture, we try to understand the application of the first law towards the non-flow system. We try to understand what is the flow system, what is non-flow system. Non-flow system we generally call as the closed system, and in the closed system we allow the transfer of energy but not transfer of mass. This we already learned in the previous lecture, how the systems are classified: open system, closed system, and isolated system. Okay, and we started to apply the first law to the closed system. Q is equal to del U plus of W, and we derived the three basic terms for three different processes which happen at constant volume, which happen at constant pressure, and which happen at constant temperature. We try to understand what is work done in that process, what is del U and what is Q. At the same time, at last, in order to solve the numerical which are based on these three different processes, in the next lecture, we are going to explore one more process that is called as adiabatic process. That is PV raised to power gamma equal to Z, and we'll solve the numerical on that. Okay. So any doubt in today's lecture?
No, sir.
No, sir. No doubt.
All of you with me?
No, sir. No doubt.
Yes, sir.
Okay. Hope all of you are also maintaining, all of you are also writing the notes. Okay.
Yes, sir.
Yes, sir.
In each and every lecture, we used
Yes.
to do such type of the treatment on the topic. So if you take down the things in your notebook, then your notes will also get ready side by side. So you don't require to move here and there in order to search for the different notes. Okay. So we'll stop our discussion at this end. CR,
Yes, sir.
34 students are present. So 34, 33, 32 students are present. Okay. Can you give me the option numbers, please?
So the thing is that in H1 there is land problem in 2 hostel rooms. So they had joined with means their roommates. One is Jatin Praveen.
Okay, let me take down Jatin,
Praveen.
Praveen. What is his roll number?
So his roll number. Wait, sir, I will give. So but he is there in the lecture. He was there.
Okay, I will find out from my
084.
084. Okay. Option numbers?
So he and just 1 second, sir.
Hello, sir.
Yes, yes.
He is there, sir. He is talking with Manthan.
Manthan?
Actually, my net is not working in my room, so I had to go to Manthan's room.
Okay, no problem. No problem.
Yes, sir. Thank you.
So all are present then.
All are present. Okay. Okay, so on the Moodle, I will upload one assignment which based on the derivation of these 3 basic processes. In the stipulated time period, please solve that and upload that assignment. Okay, in your portal. Thank you. Thank you very much.
Thank you, sir.
Thank you, sir.
Thank you. You can log
Thank you,
out
sir.
from the room. Thank you very much.
Okay, sir. Thank you, sir.
Thank you.